不要，为什么不要？哎，对你的 MA2有帮助，好不好？哈，你一定要拿 MA2。对呀、真的，真的，真的，真的，真的，更难，更难
哪个不要拿？
啊
哪个不要拿？
！General topology
那你不要去啊！
没有，你学了你就不用学 MA2了，你学一个可以考2个试。
看看如果我们白拿的话，他就真的假的？不要跟我，叫我拿的还是别的老师很酷哦。
我不会 scan
哦，可以
很丑哎。
有名的。
黑色我们答应先。
那没有
是这样吗？然后到时候我就把这个挖填上。你要我把这个挖填上去。啊，不一样。
你现在还想跟我们吃饭呢，还叫我们去拿你的手？
还有我感情问题。
哎呀，我想跟吃饭就拿月饭，那你不要。
要 monitor 你们的感情问题。
我跟我们也是模拟这些感情，所以我们应该要拿吧。不要模拟你的感情，所以我们现在拿。
其实我们模拟还多一些，但其实。
什么课？不知道，打算开新的，不知道有没有开。嗯，algebraic geometry。
有可能是谁教的？
一定是你的那个老师啊。
我们专业也是这个反应。他什么意思 ？MA2 啊，他们上面讲 MA1 跟 MA2。
好，不要看他的那个 Seng，
你看他一点了。
我知道他会心软哦。
啊？
会心软哦。
什么意思呢？
我昨天去跟他考那 probability 的那个 formula sheet 嘛，因为谁我怕等下用不到，我就一点因为没有 download 到，就是然后我跟他讲说，这里还有那个什么，他讲没有了。我讲我明天要考 statistic formula sheet，我在 chat 啊，然后他就讲 I'm not your servant 的，他讲我不是你的佣，然后我讲 stat，他讲 stat because I'm not your servant，然后我就讲 stat because I don't have formula sheet，然后就 send 给我。但是我好像你的意思哦，他就代表他以前是我们的servant。是吧？现在讲 I'm not your
我有
servant，
一种还不是讨论你的感觉。
还跟我。
你怼他没？你怼他？你这样怼吧。
我怼到，别我分了。
不像他这样。
背景跟不好意思。看够哪里？
哎，怎么？
这里面的是，小声要做起来。
对啊。
导演，他不要卖给我。你那都比是那个点点，我连是中间超子风。一天吃一大包。
你试试。
2个charge让我把 WeHave 删掉。
那边旁边有一个东西可以删掉，那是 comma。
那好。
这个名字什么？然后现在我这个
而且来吹也没事。
考试不好就 set 了 ，assignment 不会做就 set 了。啊？有声，一直小秒。你要什么？Did I just finish exam? Is it? How's your exam? Huh? Good. Not good. Not good. Okay. Everything pass is pass, but you can work hard another time. Okay, it has been a long time. We come back to the lecture. So there's some update before we continue. One update is because we cancel our Tuesday class, so we're gonna replace on next Monday, 7 to 9. I will announce the venue soon. Okay. A few bookkeeping stuff. So if you look at this theorem here, we want to write Zm cross Zn as a cyclic group. Okay, if and only if M and N is relatively, okay, they are relatively, the GCD M and this one. But in our proof, we miss out one cases. Okay, so the cases that we consider was what? So okay, so the isomorphism here we send 1, 1 to 1. Okay, so when it works. Okay, so we need to check whether P has order Mn or not. Okay, so there's one case we miss. We consider P is 1, P is Mn, P divides M. And actually this one P divides N also. And the other case is, what if P divide Mn but P doesn't divide Mn? Okay. And so you know what's this example here? For example, let's say P is 10 and then Mn is, let's see, Mn should be what? is, let's say, 2 times 15, okay, which is 30. So for this kind of case, how do you deal with it? Okay, so you also show that there will be a contradiction because your 1 will go to 0 earlier. Okay. So please have a read. I think I won't go through this again in class unless you read it first. Okay, if you read it, you don't understand, then we can discuss. Otherwise, we need to restart the whole logic, which is wasting time. Okay, you can try and read it. I already put it on the lecture note already. Okay, so the key point here is if you compute the power of 1 with this smaller power here, you will go to 0 earlier. I think. Yeah. Yeah, try and read it. If you don't understand, you can look for me. No 问题。你肯定是看不懂，我就叫你回家看见。肯定看不懂，因为我什么都没有讲，我只是告诉你我们少算一个 case，然后我已经把这个算法写给你了，所以你先读一读 ，OK， 读不懂再来问我 ，OK， 然后我们可以再讨论 ，OK， 因为如果我现在讨论的话，我们要从头讲整个东西，那我们就会花时间 ，OK 吗？所以我现在告诉你的一件事情就是，我们少 consider 一个 case，OK， 什么 case？ 就是 P divide Mn，but P doesn't divide M。P doesn't divide N, but still divide Mn. And then there's a contradiction again. Okay? Yeah, try and see why there's a contradiction. If you cannot see, you come and see me. Or message me. Okay or not? Is it clear? 没有欺负你哦，没有欺负你啊，你先读一读啊，不懂再来问我。Okay. I already give you the answer, so please read it first. Okay, the other case is the important thing we left over last time. It was when, so the question was, if I have a group, okay, and then you look for 2 subgroups inside. And let's say this is H and K, okay, and then you take the element here and multiply them together. And let's say you get H1, K1. Okay, so when is this HK set? Okay, when is this HK set equals to G? When can you split G as a product of subgroup? Okay, so this is the last question we asked last time. Hey, by the way, in the assignment, all of you write this kind of thing. H1, K1 is in the intersection of H intersect K. This is wrong in general. You thought that this is about closure, right? But this is closure between what? Different 2 subgroups. Closure is about 1 subgroup. You cannot just see this and then deduce this. Okay, that is wrong. Closure only happen within 1 subgroup. Okay, not 2 subgroups. Does it make sense? Okay, so if you take like H1, H2 inverse in H. Okay, so if H1 in H and also H2 in H. But now the case was 1 is in H, the other one is in K. Different subgroup. Where's the closure? If you can just close like that, then nothing, like everything can be put together already. Does it make sense? And what does this intersection means? This intersection means this element have to stay in H and K at the same time. Okay, have to stay in H and the K at the same time. Okay or not? Okay, have to stay at the same time. Not about closure. Okay, most of you write this down inside your assignment. Okay. So please don't do it again. Okay. So what's the theorem we left over? So let's fill it out. Okay, so here's the statement. Okay, so the theorem is like this. So if you start with two subgroup of G, okay, and then you have a multiplication map, you multiply two element inside different subgroup together, and you call this image HK. Okay, so note that there's two main character here. So one of them is H cross K, one of them is HK. Okay, they are different. They're different, because H cross K, the element is two doubles. Okay, and two doubles. But HK is just multiply H and K together. So if you multiply 2 and H and K together, this set should be a subset of G. Why? Close or closure of subgroup. Closure of what? Of a group. Okay, so here is by closure of a group, not subgroup of group G. Okay, because what you multiply is everything in G, still in G. Okay, because LOC is a map from G cross G to G. Okay. Hey, by the way, Zihao, is it Zihao? Yeah, Zihao asked me about the universal quantifier thing, right? Later I will address it. Okay, since we already start this one. Next hour, I will start with that. Okay, remind me if I forgot the universal quantifier thing. Okay, right. So this H times K is in G, H cross K is another set. Okay. So the last thing here was D. So we are interested in D. When you can write your G as a product of two subgroups. Okay, when can you do that? If and only if you check their intersection is only identity, and then the image HK is exactly G. Okay, sort of surjective. Okay, surjective, right? Image is the whole thing. Okay, and then H and K have to be normal. So, I mean, well, what's this isomorphism here? Whenever we talk about isomorphism, right, we need to tell you what's the map for this isomorphism. So what's the map here? Is the F. So what's F here? F is a map from H cross K to G. Okay. So to be an isomorphism, what's the definition? What do you need to satisfy? Homomorphism and bijective. Okay. So why? So I define as a map. Just multiply together. Why is it a homomorphism? Can you see from ABC which line tells you when is it a homomorphism? B. Okay. B tells you when is it a homomorphism. If and only if for all H in H, for all K in K, HK equals to K KH. HK equals to KH. Okay. And do we have that?还是指明哎，长得很像指明。Yeah. So do we have that or not? D. Do you see? Do you see? How do you see B from D? How do you see homomorphism from D? From this condition here, H and K are normal subgroup. Can you see or not? seem like a bit non-trivial, huh? A bit non-trivial here because why? Normal just tells you what? H, K, H, maybe it's just another K. But why is it the exact K? H, HK, H inverse should be another K, right, for normal. But why is it the same K here? Okay, a bit non-trivial. We need to prove it. Okay, so later we will see how to prove it. Okay, so if we settle homomorphism, do we have injective or not? How do I to get injective? A. So when is it injective? When the intersection is 1. So if you have the intersection, it's only the trivial subgroup, then you have injective. Surjective? That's surjective or not? Which condition gives you surjective? Huh? You have H, the E match equal to the codomain. Then E match equals to the codomain. Okay? Right, so there's one non-trivial thing you need to do. Why HK have to be equal to KH? Okay, so let's prove all these statements quickly. Okay. Right. Is your brain working today or not? Try to work. Okay, let me work. Okay, so let's start with this. So this is a if and only if statement, right? So we have to prove two directions. So right to left, left to right. Okay, so if H is injective, how to prove the intersection is 1? So instead of doing the direct proof, we will do contra positive. Okay, so contra positive means what? If the intersection contains other thing than identity, I want to prove that it is not injective. Not injective means what? Not injective means what? Two different things get sent to one thing. Okay, so if there's extra things there, can you create two things that get sent to one thing or not? Okay, let's try. So suppose hash intersect k contain some x not equals to 1. What's the two things can get sent to one thing now? Well, I mean, so we know that f11 is what? 1 times 1, which is 1. Okay. So can you play around with this x or not? Such that you have another thing that sends to 1 also. What's the two things that you can multiply together, you get 1 using x? Inverse. Okay, so let's see. Also, we have f(x) x inverse is equal to x times x inverse equals to 1. But the question now is, the first coordinate here have to live in h. Okay, second coordinate here have to live in k. So do we have x inverse live in k? Do you have x inverse live in k or not? X live in where? In the intersection, meaning what? X live in h, x also live in k. So the question now is x inverse live in k. Why? Because k is a subgroup. Okay, so inverse exists. Okay, so yeah, so done. In this case, done. So f is not injective. Add here x in h, x inverse also in k. Okay. How about the other direction? How about the other direction? Suppose that the intersection is 1. Okay, what do you want to show? We want to show that the map is injective. The map is injective means what? I want to show if f of h1, k1 equals to h2, k2. This implies that, implies what? h1 implies what? The tuple have to be the same. But the tuple to be the same means what? 怎样说两个 tuple 是一样的？每一个位置都要一样。They have to be the same component wise. And so h1 equals to h2, k1 equals to. Okay, so do we have that or not? So if, so since f h1 k1 equals to f h2 k2, this implies what? What's the definition of f? It's just multiplication. Okay, so we have h1 k1 equals to h2. Okay, but what else we can play around with this? A bit similar to assignment thingy. So what can we do here? We can group all the k together. We also can group all the h together. What's the usefulness of these? I can see 一堆 h 在一起，一堆 k 在一起，他们要活在哪里？ The right hand side here says that this element have to live in h. The right hand side here says that this element also need to live in k. Okay. So this is how you deduce they live in the intersection, not using the closure of the subgroup. Okay, because now you can use closure of subgroup because they are living in the same group. Okay, so they are living in the same group. So meaning what? This means what? K1, K2 inverse will live in K intercept H. Okay. Also, H1 inverse, H2 also live in the intersection. Correct? Okay, because K1, K2 squared, K1, K2 inverse, I know live in K, but I can write it in the H form. Then it lives in H, so at the same time live in H. Okay, and then H inverse H2 live in H already, but I can write it as a K form and then live in K. So they live in the intersection. But what's the one thing we know about this intersection? Suppose the intersection only contains identity element. So meaning what? These two elements has to be the identity. Okay, so this implies that K1, K2 inverse is 1, H1, H2 inverse is 1. So you get that K1 equals to K2 and then H1 equals to H2. Okay, so you get injectivity. Okay, and maybe you ask a question. 老师，我们不是证过了没 ？homomorphism injective 的话，什么？它的 kernel 是 identity， 所以这个是它 kernel 吗？ Is it? Not sure. 是咩？证过了咩？ So if you want to use that, you need to answer two questions: whether this intersection is a kernel or not, and also F is a homomorphism or not. Okay, so you need to settle this problem. Only you can use the equivalent property of injective. Okay, maybe look very similar, but you need to be a little careful. Okay, so really, we just start with map. Okay, F is just a map. No homomorphism yet. Okay. Right. Right. How about second statement here? Let's do a second statement. Okay, so second statement here talk about homomorphism here. So well, why it can be a homomorphism? Because we know that both of them have to be group for the domain and codomain. G is a group. H cross K, how is it a group? We defined last time, product of two groups. What's the LOC? Answer me. What's the LOC of product group? Sorry? Pardon? Can I understand? So the question was, H cross K, why is it a group? Why H cross K is a group? How is it a group? So you need to tell me what's the LOC. How to combine two elements. How to combine two elements. So if you take H1, K1, H2, K2, how do you combine them together? What's the natural way to do it? Yeah. Yifang. What's the natural way to combine these two elements? Sorry? Linear combination? 你讲 linear combination 啊？你讲什么？我没有听到 ，sorry。差不多，怎么样 linear combination？你是说开挂弧啊？怎样做啊？啊？还是 ratio 类 ratio？ You just multiply component wise, okay? Component wise. So you do the first one multiply with the first component. So this one is using H LOC, and then the second one you just use K LOC. Okay, component wise. Right, and then we prove that there's you have inverse also, you have identity also last time. So when is it? So when is it a homomorphism here? So what to check? So let's do a proof here. That H1, K1, H2, K2 be two elements inside H cross K. What do you want for a homomorphism? You want that H, so we want what? H of H1, H2, K1, K, sorry. Wait, let me think. So what do we want? Right. You still remember what's the homomorphism definition? So let's write down that first so that we don't confuse ourselves. So P from G to G prime is a homomorphism if for every A, B in G, P of A, B equals to PA times P, B. So what's PA, P, B here? So we have, let's say H, F of H1, K1, and then times F of H2, K2, okay, is equals to what? F of the multiplication of two elements here, which is H1, H2, K1, K2. Okay. So this is the question we want to get. But to solve this means what? By definition, it's just H1, K1, H2, K2 equals to H1, H2, K1, K2. Okay. But can you see anything here or not? To get this, what have to happen? Can you cancel anything extra here? Can you see? You can cancel H1, right? okay, by multiplying H inverse, and then you can cancel K2 also. So in the end, what do you get? K1 and H2 must commute. Or H1 and K1 must commute. And then this is a if and only if, right? So if you want to have this, you can deduce the last line, and then you have the last line, you can deduce the first line. So if and only if statement. So we are going two direction. Okay, so going two direction. Does it make sense? Okay. Right, so we have proved this. Next is we want HK to be a subgroup of G. The image of this map to be a subgroup of G. Okay, so the third one. So let's do the third one. Let's do the third one. So to prove a subgroup, you need a few things, right? What things you need? Before the exam now, what things you need? Remind yourself. You need closure, inverse, identity. Okay. So you need to prove all these things. Right. So which one is easier? Which one is easier? Which one is easier? Identity can find or not? How to find identity? Is identity inside HK? How? You can write identity as identity times identity. Okay, and then hash and K contains identity. Other things, Other things, Other things, I think we need some extra stuff. Right, so we need some extra stuff here. So look at H is normal. Okay, if H is normal, what do we know about a normal subgroup? What do we know about normal subgroup here? Then for every K in K, KH equals to H. Normal subgroup, right? Or equivalently, I gave you HK, KHK inverse equal to H. So they are equivalent. Right. So how to show closure? So let's write down something here. So for every xy in HK, you can write it as xy is in HK. But how does this xy looks like? How does the xy looks like? Sum h1 k1 and then y is equal to sum h2 k2. Okay, and then what do you want to show? You want to show that, for example, h1 k1 h2 k2 is in hk. But what's the problem here? Did you see a problem here? You need to write everything in h first and then multiply by k. But here, mix up. Got h for k, got h for k. Is there a way to swap this hk or not? Is there a way to do it? 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 So how to do it? way to do it. We can replace K1 H2 by H2 K1. H2, the exact H2? Not really, right? Maybe it's another H coming from H. So maybe there's a, for example, K H3, again K1. Okay, no, by the normality. So I mean, in general, we can write like this. You take HK equals to HHKK. Okay, and then equals to HK. Okay, so we use set equality to do it instead of looking at this horrible element. Okay, does it make sense? Okay, so this is a set equality to show this kind of element wise. What happened element wise? Similarly, inverses. So if I have HK inverse, what is it? It is K inverse H inverse. But this guy live in where? Live in KH. However, we know that KH is equal to HK. Okay. So if you wonder how we relate this HK KH thing to this equality here, so we just note that KH is just union of all the coset. Okay, little KH. And then HK is the union of a little right coset. Okay, so they are just union of all. That's all. Okay, because obviously this one live in K inverse H, right? But K inverse H is a subset of KH. I just look at it. Okay. Does it make sense? Any question so far? Question? Any question that you're not sure? Is it clear? Okay. Yeah. Right. So we have done showing this image of this homomorphism is a subgroup if H is normal. So in last line here, we have all the nice property with us. Okay, we have nine property with us. The only one thing that is non-obvious is what I told you just now. Okay, so let's do it. So which one is obvious? Wait, let me repeat again. Right, so let's prove D. So which direction we should go first? Let's go from right to left. Okay, like what we said just now. So from which one? From A, we know that the intersection is a trivial subgroup, implies that F is as this one is injective. Okay, it's an injective map. Okay, how do we get homomorphism here? This part is non-trivial. So how about we left it first? So okay. Also HK equals to G implies that F is surjective. Okay, then we are left with homomorphism only. So what to do here? To show homomorphism, okay, to show homomorphism is a homomorphism. What do we left to do? By part B, we need to show that prove that for all H and K, okay, obviously they have to live in a different space. HK equals to KH. Right. How to do this? this. So one thing that remember how we reached this kind of property here just now? We do this, let's check. So we did cancellation only. Okay, never mind that. Okay, never mind. So here's the trick. So what's the trick here? Right, we want to show this are equal, right? Can we do something else? For example, let's play around with this guy. So hk equals to k, h means what? You need to show that hk, h inverse, so let me see, h inverse, and then k inverse is identity. Okay. Right. This guy is identity. Do we have this condition or not? Think about it. Okay, do we have this condition or not? So we know what? We know that k is normal, h is normal. So there's a lot of conjugation happening here. Okay, so at least two conjugation happening here. So you can conjugate k with h, conjugate h inverse with k. Okay, so if you look closely, what happened here? So if you look closely, there are two ways to read this. Actually, this is what we call a commutator. Actually, commutator. So this is a definition. Okay, by definition, this is what we call a commutator. So why do we call commutator? Commute, right? So it must tell you something's commute. So if this commutator equals to 1, you can see that h and k commute. So we call this this part here commutator. Okay, this hk, h inverse k inverse is called commutator. Right. So if you look closely, there are two ways to read this commutator here. So you see the conjugation from on k and then the conjugation of h. If you conjugate k with h, where should this element leave? Well, we know that by assumption, h and k are normal subgroup in G. Okay. So the first bracket here, where is it? Where does it live? Wait. K is normal. So you conjugate with element in G. Living where? GK G inverse equals to K. So here live in K. Okay. So the first part here live in K. Okay. Second part, second bracket live in where? H. But on the right hand side, you are multiplying everything in K. On the left hand side, you are multiplying everything in K. On the right hand side, you are multiplying everything in H. Meaning what? This is another element living in where? H intercept. Okay. But by assumption, what is inside H intercept K? Only the identity element. So since H intercept K only contain the identity element, this element have to be equal to the identity element. So you really have HK equals to KH. Okay. Does it make sense? Okay. So you have quite a strong condition here. So if H and K are both normal and then the intersection is 1, then you really have HK equals to KH. Because the usual normality, you only get H1, K1 equals to maybe K1, H2. Yeah, but if you have extra condition that both of them are normal and then the intersection is only to trivial group, then exactly equal on the nose. HK equals to KH. Okay, in other words, they commute. Okay, so we will stop here for this proof. Okay or not? The other direction I left to you. I think it's an easy computation. Okay, the other direction is easy computation. So assume you have this isomorphism and then prove this condition. Very easy, I think. Can or not? I actually proved the answer to you already. Okay or not? Can leave it to you. Exercise. I prove to you a lot of statement already. I left the last one to you. Okay? As a homework. Can or not? Okay. Okay? Yeah, try and do it the other direction. I think it's easier. Okay, the other direction should be straightforward. Okay, 蛮直接的. Okay, you just check whether you have this set equality or not. This set equality. I mean, this set equality is obvious, right? Because your map is already surjective. So the image must be equal to G. So you got one done. Okay. And then first one, again by part A, because part A got two direction, right? Injective implies the intersection is equals to one. And then I think non-obvious one is to show these two are normal. So this is the only word you need to do. OK 了，可以吗？最后一个让你去 try 一下。OK，可以吗 ？OK 啊，I let you try 啊。I give you answer also in the lecture notes. So you just left to show h is normal. And then I can tell you another hint. Once you can show h is normal, k is normal is the same. So you really need to only do one more thing, just to show h is normal. To show h is normal, what do you need to show? G hash G inverse equals to h. Okay. All right. So let's continue first. Okay, let's continue. I think we need to finish out some important statement. So this one is very important. So there are, finally we come to this statement that I gave you 2 weeks ago. So there are two isomorphism classes of group of order 4. Okay, one is what we call a C4, and then the other one is what we call a C2 cross C2. Okay, last time we write it as Z2 cross Z2 with the addition here. And then the other side, we write it as Z4. We use the plus here, also addition here. Okay, so the first one, why I put C here? Because this represent, let me define it. This represent the cyclic group of order 4. Okay, is Z4 a cyclic group or not? Z4. Is Z4 a cyclic group? Right. So generated by what element? 1. Okay. But when I put cyclic group, right, this means what? This is a group with a generator, let's say X. Okay, a random one. Okay, no need to be any specific element. Okay, and then the other one, is a product of cyclic group of order 2. Okay. Okay. Right. But on the Z4 side, we have the generator to be 1. So we abstract these Z4 group here, abstract to a group that is generated by 1 element. And there's in total only 4 elements inside there. That's all. Okay, this is what we want to see. So let's prove it. Okay, let's prove it. Okay, before we prove it, this is what we call a Klein 4 group. There's a name for this C2 cross C2, Klein 4 group. Okay, yeah. Klein is kind of famous. If you go to algebraic topology, I think you'll learn something called Klein bottle. Klein bottle. And there's a relation between Klein for good and Klein Bolter, I think. Right, so let's prove this. Why in this world there's only two isomorphism classes here of group order 4? So let's G be a random group order 4 here. We want to show that it is either C4 or either C2 cross C2 here. Okay, so we prove Lagrange theorem, right? What does Lagrange theorem tells you? The order of any element x of G must divide the order of the group. In this case, is what? You have to divide 4. Okay, you have to divide 4. So there are few cases to consider. Actually, there are only 2 cases to consider. Let's see whether these 2 cases cover all the situations. So case 1. If G contains an element of order 4, we claim that then G is a cyclic group of order 4. Okay, is this clear? If an element has order 4, meaning what? Before reaching 4, it will be a different element inside your group. But if it only equals to 4 during, so let's give you an example. So x, so let's say there's a x, so let's say this element is x. X is just x. So let's say x is not identity, obviously, because otherwise it won't be order 4. And then x squared is another thing, cannot be identity. Cannot be x also. You know what happened if this equals to x? The order will collapse. Okay, so one thing you have to know is x squared, if the order is 4, you cannot be equal to the previous element before the power. Otherwise, this will imply what? X equals to identity. So you reduce the order. Okay, so we have x squared not equals to x. S cubed, also not identity. Also, you should know that this s cubed cannot be s squared and x either. Otherwise, you can play the same game. Okay, so really, these 3 elements are really different. So before you reaching the order, right, they are all different elements. Power of x should be different elements. Okay, and then, so how many elements you have already? 1, 2, 3. The 4th one is identity. So you have an order 4 group already, cyclic subgroup. Then this is the cyclic group of order 4. Okay, is it clear? Okay, how about case 2? Let's say, you see, now we assume there's an element of order 4, right? Case 2 was, let's say there's no order 4 elements there. Okay. For every element of G except the identity has order 2. There's no one has order 4. If you have order 4 elements, then your group is a cyclic. But let's say all of them are order 2 except identity. This means what? In this case, okay, let's call it x here. In this case, all the x will be x inverse. Is it true? True or not? How to get this line here? To get this line, what do you need? You need x squared equals to identity. Because they are order 2, ma. Correct. So x is inverse. Does it matches with your transposition? Sn. What's the inverse of a transposition? It is itself. Okay, why is it itself? Actually, because your transposition has order 2. So actually, it's the order 2. It's not about swapping. It's about order 2 actually. Alright, it's not about swapping 1 and 2 twice. It's because the order is 2. Right. And then what else you can do here? So let's take two elements which are different that's not equals to identity. This is not transitive. I don't want to write like this. And xy is not identity. How about write like this? Not identity. Okay. And then very troublesome. Let's take x, y, and g such that x, y is different and then x, y is not identity. What can you do here? Then we claim that x, y also has order 2. Can you see this or not? Can you see why x, y has order 2? Why? Sorry? X, y is in G. Good. Right, good, very good. Okay, because x, y is in G. What do we say? Every element that is not identity has order 2. Okay. Order 2 means what? So this implies that xy is identity. Also implies what? Xy, y inverse, x inverse is, sorry, xy equals to y inverse, x inverse. But what did we deduce just now? What is y inverse and x inverse? Itself. So what do we have? We have xy equals to yx actually. This implies what? This shows that xy commute. Okay, xy commute. But this xy is general xy. So this means what? Hence, G is abelian. G is abelian. And G is abelian. Now come to the reason why we introduce the proposition just now. Okay. So what can we do? What can we do here? So every subgroup is normal in this case. Okay, every subgroup is normal. Okay, because because to show normal is means what? GH G inverse equals to H. But now it's abelian, right? GH must be equal to HG. Okay. So it is normal. We are going, let me hint you, we are going to use this. Okay? We are going to use this. Okay. Right. So you should think that this H and K is C2, C2. Okay. H and K is C2, C2. Right. And then G is our that has element with order 2 only. Okay. Now every subgroup is normal already. Okay, what we left to do is to check these two properties here. Okay, so that we can split our group into order 2 subgroup. So we need to build order 2 subgroup here. So the claim is like this. So we can choose x not equal to y. So let's choose the xy in G. Do we have to choose again? Let me see. Okay, choose again. Let's choose again. Let's choose such that x not equals to y, and then they are not identity. Okay. What can we do? Let h equals to the cyclic subgroup generated by h, sorry, x, and then another cyclic subgroup generated by y. Okay. So these two are order 2. Because all the elements which is non-trivial here is order 2. So these two are order 2. Not that trivially h intersect k is the identity. Is it true? What is inside h? What is inside k here? How many things inside h? How many things? 2, right? Identity and x. The other k, identity and y. But we already assume x is not equal to y. Well, let me ask you another question. Can you make sure that we find these two elements or not? Can you make sure this? We should. Can we make sure that we find these two elements that's different, but they are order 2 in G? 做得到吗？这件事情做得到？为什么？为什么？啊？为什么做得到？做不到就事情大条。My group contain how many elements? 4. One of them is identity. 3 of them must be different, and they have order 2. 从这3个里面选2个就好了。OK， 全部都是 order 2，随便选2个，3个里面选2个，肯定选得到。对 ，OK，pigeonhole 对吧 ？pigeonhole。OK，and what? And another claim was HK is equal to G. Okay, this is the claim. HK equals to G. What is HK here? HK 里面长成怎么样？有什么可能性在里面？来，少奇 ，what's the possibility of HK if I have 2 element set for both? E, X, Y, X, and Y. Okay. So there are 4 elements here. Okay. So what you need to show is, you need to show that this XY cannot be X and cannot be Y. Otherwise it will collapse. Correct or not? We know that X and Y is different already. E obviously different from 3 of them. But you need to show that this XY cannot be either one of them. Okay, otherwise, what happened? This set will only contain 3 elements. Okay, so you need to, one thing to show this equality, you need to show that XY is different from the other 3. How to show? Contradiction. Suppose it is one of them. Okay, if xy is equals to E, what happened? X equals to Y inverse. But Y inverse equals to Y. So contradict X not equal to Y. If xy equals to X, we will find that Y is actually identity contradiction. Similarly, if xy equals to Y, contradiction also. Okay, so they have to be different. Okay, so they have to be different. Okay. Since xy not equals to E, not equals to X, not equals to Y. Okay, otherwise you get contradiction. And then, so basically we are done. Okay, so we are done. So by proposition part D, what do we have? We have G is isomorphic to the order 2 cyclic subgroup generated by X and Y. Okay, so this is basically the C2. Okay, cross C2 here. Okay, any question? 问题吗？所以我们刚才证的那个 proposition 是有用的，我们就是拿来证这个。Okay. And then let's finish up some content and then we will take a break. So I just let you see here. So these are not examinable, but I want to tell you the full story. So here is it. So in general, if you look at a finitely generated abelian group, okay, just now we only generated by 4, okay? Yeah, generated by 1 element, okay? 1 or 2 elements, okay? So finally, in general, finally generated abelian group, you can write it in this form here. Can you recognize this form? So what's this form here? So for the first part here, it is finite group. Okay, finite group to what n here? This n is very special. Is the power of prime. 知道吗 ？assignment 有做吗 ？power of prime. Z of power of prime. And then multiply with Z. Okay, so Z here means what? Is a infinite group, right? First part here is finite. The second part here is infinite. So you can write it as a finite group part and an infinite group part. Okay, so the finite group part you will split into power of primes. Okay, power of primes. Okay, but infinite part you depends on how many z you have. Okay. So how to prove this? We won't prove it. Just give you an idea. We can split any finitely generated. So let me draw the main point here. So we can split finitely generated abelian group as a product of finite group and infinite group. Supposingly using the proposition just now again. The first part here is what we call, the mathematician call here torsion. Torsion part. Not torsion, torsion. Torsion. T-O-R-S. Torsion. Okay. Yeah. After certain power, it get killed. Okay, torsion part. Okay. So you should imagine that these are the generators of your group. Okay, like just now. And then second, we will say that a group is decomposable. Again, if it is isomorphic to a direct product of two proper non-trivial subgroups. Okay, so for example, just now, we can decompose every finitely generated abelian group. Okay, we can decompose. And then what's the theorem here? The finite indecomposable abelian groups are exactly the cyclic group with order of a power of a prime. Okay, so I include some proof here. And the last theorem before we go to next section was if M divides the order of a finite abelian group, then G will has a subgroup of order M. Okay. So meaning if you have a abelian group which is finite, okay, and then you count what's the order because it's finite, right? So there's a order. And if there's number M divide this order, you can find a subgroup of that order inside the group. So I put the proof here also. But these are not examinable. Just that I want to tell you the full story. Up to here. Any question? So basically, what we have done is we have looked at a multiplication, kind of a multiplication operation of group. We take product of group. Next section, we will take quotient group. We will do quotient group. We're kind of dividing group. Okay. So everything you can do on number, we are sort of doing it on groups. Okay. Any question? Yeah. Thank you. Okay, if no question, let's take a break until 6:90. 6:90. 你要哪一个？下面这个。OK， 那个是叫入定。定什么？喝水。哎，我笔一直不见去。 啊，红笔、蓝笔全部不见去了，来点名了。我没有讲，我是跟你讲，我笔不是吧？
我突然想到非二乘那个贼二乘贼二是一个反。
你说 GHG inverse
不是，我是说上节课那个
哪一节课？
周一的那个，
你讲那个考试题啊？
不是那个考试，就是那个 Z2 有4个元素，然后它里面有3个 order 2的 subgroup，
然后呢？
每个 index 都是2。
啊，那个我知道啊，但是问题是 GHG inverse 不会去到另外一个 subgroup，
会去吗？
因为它 Abelian。
我是说那个题肯定是对的呀，我只是在说你上课的那个证法错了。
哦，但是我是说 GHG inverse 也不会去到另外一个 H， 它会回去那一个 H。
但是你是在用 reason 是吗？
对啊，对，你要 GHG inverse 不回去那个 H 吗？
不回去那个 H 它不就不 normal 了吗？那你是在否定这个命题啊，不是在否定你的证法呀。
不是，我要找的反例不是 GHG inverse 不回去那个 H 吗？
你要是不回去，它就不是 normal 的。
对，
你已经证明了每个 order 2的都是 normal 的呀，所以你怎么可能在这个地方找反例呢？
所以反例是我们现在，对反例是我们。
但是我觉得你那个证法没问题，有错呀，你没有办法直接说明它会回去。
对，但是你举来这个例子，我还是要回去，因为它是本地。
我的意思是你证了它是 automorphism，你只说明了它 GHG inverse 的 order 跟 H 肯定是一样的。但是我的意思就是说你的 order 一样，你不能直接推出来它一定是 normal 的。
对，
不是说我要去找，我一定要不是要找，
是要讲分。
所以就用你后面答案给的那个方法了，不能用你上课那个方法。
哦，好。但是我在想
你要懂我
怎样去来讲它是错。
就我刚刚这个例子就告诉你，它 order 一样，它也可以是2个 subgroup，
嗯，
但是不一定要回去啊。
但是我用的理由是它的 intersection 有 identity， 我不是用
我刚刚举的那个例子，它不是 order 一样，然后 intersection 有 identity，但是它就是2个 subgroup 了。
啊，OK，
好，对吗
OK，对
？OK，
，OK，好。
还有你刚刚最后飞快过的那个东西，我没完全 get 到。
呃，
首先我有点忘了什么叫 finitely
就是它的 generator 就有 finitely
啊。
中文要乘这个东西，
嗯，
中文要乘后面的这些，
因为你假设你的 Z 是其中一个 finitely generated Abelian group，Z 就是 Z 了，Z 啊，
啊哈，
它这个 finitely generated 不是说这个 Abelian group 是 finite 的 group，
就是像 Z 它也是一个
Z 是一个 finitely generated，
就它的 generator 是 finite 的，不是这个
对，
你这个定理下面有写证明吗？有写的话我回去。
没有证明
你能写一下吗？
啊，不能，
那你给我发一下。
很长。OK，
回去闲的无聊的时候啥时候想读就。
讲
课本里面有
哦
叫生还是法雷其中一个。
，OK，
然
然后我回去找找，然后给我
怎么
你讲哎，
讲什么？讲什么？哎，红杰来了又不见了。
他来了吗？没来吧？
有，刚才看到了，
在哪？
打了。为什么？
可不可以的5方人？
为什么？不要睡觉。OK。
下课
举报你
老师所有的里面。
确实。啊？
怕人家举报你哈，
什么？
怕人家举报你，
也不是举报，我要赶工。要拖堂哦。
到9点，9点拖堂。
要拖堂哦。
人家是玻璃心刀。我以为我会有。下一堂课。
你还有下一堂课？哦。几点到11点？
对啊，今天是几点的？今天是5点到7点。
老师，我下堂课才开完。
小杨，红杰有在吗？啊，有我看到了。
为了考试。
子航，金鱼，OK，一层带一层，带一层有在吗？带一层，带一层，没有在。心仪和心仪，孙佳怡。钟一凡在吗？刘金鹏，刘金鹏没了。
他们要
所以，有啊，这边林晶，可以过来一下吗？
为了为什么会要成这个？做的问题尽量做了。
可能我在是因为他有可能是他翻的不是 generator，就是那个 generator，本身就是一个环境。
线，为什么后面我们是分号这
我也在考试。
Yeah, I think your previous assignments the result a bit drop I think from how you do it right, a bit rush you guys do it, is it? 很紧张吗？你们做那个 assignment 的时候，很多东西漏掉啊，写不好这样，做到很赶了，做到很赶是吗？做到很赶，因为有其他 assignment 还是怎么样？MA 啊，呀，因为我放出来3个星期嘛，那个 assignment，所以就如果我早放，不是你如果就算没有做完，我希望你先看先 ，OK， 先看先，好，呀，先看先啦，不要到最后一天，不然的话全部挤在那边了。你可以先看，不要写先也可以，但是先看，大概知道要做。看回来了。Yeah, I just returned to you this afternoon. Yeah, I should be able to check it now. Okay, so the mean is at around 73. Okay, mean is around 73. I think we got a few high scorer 44, 45, like Pang Xing and then who else Eric Yi Chen finally got full marks. And then Su Yao also improved quite a lot. Su Yao, yeah, improved quite a lot. Hong Rui, usual Hong Rui. And then Lydia, Lydia finally climbed to the top. But she's not here today. OK，有些人有点退步啊，所以大家加把劲，有努力，好不好？要考试了。OK，在20分那里附近呢，要小心一点。OK，努力啊！有问题可以问我啊，读不懂的可以听我，我有空我可以回你。我告诉我另外一个班呢，我不知道你们班我感觉你们班还比较好一点吧。但是数学系里面哦，很多学生喜欢做的一件事情，你们知道是什么吗？啊？数学系的学生喜欢做一件事情，你们知道是什么吗？2个字，内耗。OK， 千万不要做内耗的事情啊！你可以来问我，可以问你的同学。OK。没有误解。
没有误解的是
情感，
没有误解的情感。
OK， yeah. Also, Hong Rui help to do extra exercises, and then we should expect quite a complete solution to our theme. Okay, until chapter 2.8. So you please read them. If you don't want to do it, please read also. Okay, prepare for your exam. Okay or not? To prepare for your exam, make sure you know how to use definitions. Very important. Whenever I throw you a word, abelian, okay, you need to write down what's the definition and then identify how to prove it. Want to show something is abelian, okay? Want to show something commute, something associative. Okay, this word is very important. You want to include it in your cheat sheet. Okay. Right. Hey, just now some people ask, why is the Z here? So why is the Z here? This Z is natural because Z is a finitely generated abelian group. I didn't say the group have to be finite. I just said it is finitely generated. Okay, meaning the generator is finite self-generated. For example, Z is a finitely generated abelian group. Why? Because Z is generated by one element because it's a cyclic group. So that's why Z here. Similarly, ZPR1 obviously is a finitely generated group, also generated by 1. Okay, just that the order is Pi to the power Ri. Okay, right. Before we start the new thing, let's address the question of universal quantifier. In particular, I want to do it on your assignment thing. What's the question? Showing something is cyclic. What's the condition? Okay, suppose G is cyclic and phi from G to G prime is a surjective homomorphism. Okay, and I want to show that if G prime is cyclic, then G is cyclic. Okay, so a general answer, what you say, you just spell out the definition, you really do what I say. You just spell out the definition. So you say that since T is surjective for every y in G prime, there exists x in G such that Bx equals to, and then what you do again, since G prime is cyclic. Hey, I swapped the order, right? So here is G, here is G prime. Then you said that for every x in G, there exists n in n such that x equals to what? Right. So we need a generator here. So let's get a generator. So let's call it G. It is G to the power n. And then, so you conclude that P Gn equals to 1, which is y equals to Pg to the n. Any problem on this proof? Looks perfectly nice. 是吗？好像都是你们就是这样写吧，对不对？全部人都是这样写的。I mean，哦什么？你懂我意思？你说说看。
就是因为你下面说任意 x 的话，其实你是在说白了就是给它重新定义过，是你上面拿的那个 x。
不一定是，
不一定是。
不一定是 ，because this one is a general statement here. General statement. But the top here is really specific. This is a specific x. Okay, how do I emphasize this specific x? Usually we will write like this. X subscript y. Depend on y1. Okay, you give me a y, I can find you a x that depend on this. Okay. And then what you need to do, actually you need to use this assumption here. From this xy here, so since G is cyclic, you need to say as xy is in G, there exists a n depending on xy, such that xy is equals to G to the n. Then this n is dependent on xy. 你明白吗？ This general statement here is general 的，很 general， 告诉你说每一个都可以找一个。但是现在你要找到真的是对应这个 xy 的那一个， so you need to fix your xy first. After you fix your xy, you can use this statement because it satisfies this condition. For every x, you can find an n. 你明白我讲什么？你还记得上次我回答那个赵胜的问题吗？赵胜的问题不是赵胜的问题，其实是赵胜的问题，但是我没有讲是赵胜的问题。但是赵胜写了很搞笑的两句话，就是 since G is cyclic 啊，他写了两个 equivalent 的东西出来。我知道他要表达什么，但是就是不太对。这两句没有差，你明白吗？意思说 ，for example 啊 ，I can replace this x with y。Then 你又讲，如果我这样写的话，我就 prove 不到了咯，因为我上面找的是 x 嘛，下面讲的是 y， 这样不是很没有意思。You understand what I say or not? You understand what I say? Why we can use this statement? Exactly because we know that the x little y linked in G. Then we can use this statement already. I don't care this one y m n 盘星Adrian for every Adrian in G. 我不管 as long as this guy here is linked in G, I can start using this statement already. You understand or not? So you need to start with something that exists first. Then you can use this statement. Okay? Does it make sense? 懂我在讲什么吗？Universal quantifier statement and proving a quantifier statement. Universal quantifier statement. 什么 ？Okay. So well, you really need to fix xy first. Okay, and then start finding what n you have. Okay. So really, if you want to say that G is cyclic, sorry, G prime is cyclic, this is equivalent to for every G in G prime, there exists an x in G, and also there exists a n in Z such that let's put G prime here. G prime equals to phi of x, which is equals to phi of x to the n, which is equals to G to the n, which is equal to phi G to the n. So this is the full statement you need to produce actually. 看到吗 ？For every G prime 要 exist 两个东西。How to get the second existence? You use the G is cyclic. Okay, because this X live in the cyclic group already, so you can find another M. 看明白这个东西吗？有问题吗 ？Okay, so to be precise, we can write X depending on G prime, and then N depending on XG prime. Okay. To be precise, you can write this. To tell you where this existence come from. OK， 告诉你这个 existence 是谁给你的。OK， 第一个 existence 是从 G prime 给你的，因为是 surjectivity。第二个 existence n 的从哪里来的？是因为 G 是 cyclic，and then 这个东西活在 cyclic group，so depend on 这个。看到？哎，这个东西其实很重要哦，因为在你们的比如说 continuity 跟 uniform continuity 啊，两个都是要找delta。好玩了，这两个都是要找delta，但是问题是哦 ，continuity 的 delta depend on x and epsilon，uniform continuity 的 delta only depend on epsilon， 所以很重要，每一个都是 for every epsilon there is a delta，for every epsilon there is a delta， 什么 delta 呢？一个 delta 要 depend on epsilon， 一个 delta 要 depend on epsilon 和 x，OK 了。所以这个是一个比较重要的东西，在 proof writing 里面。Okay, very important. Otherwise, you'll keep confused. Okay, what you have, what you don't have, how to get things， 肯定 confused 的。如果你没有搞清楚这个 ，OK， 你会不知道你有什么东西可以用，你不知道为什么可以找到。Okay, so yeah. Okay. Got question regarding this? Okay, ma'am. Okay, so basically the question one asks you to find this guy here. Okay, you can find this guy. If you can find this and then you write out this form, then it's cyclic. Okay. So basically this G prime is just generated by Pg. Where? How do I get this G? Where? 这个 G 就是这个 G 就是 G 的 generator， 看到吗 ？OK 啊，可以想到这幅图画吗？一定有图画的，一定要画成图的。So we have G prime here, okay, and then we have G here. Okay, so what's the situation in G? You have identity, you have G square, and then G 3, and then so on. But what happens here is, if you look at all the let's say identity G prime 1, G prime 2, G prime 3, G prime 4, for example. So there's a map going from G to G prime, but this is a surjective map. So meaning what? If you look at all these Gi prime, they are coming from a element in G. Okay. So okay, our map is called phi, right? So let's say this one phi G to G1 prime, for example. And then the other one, let's say this one is coming from G2. Pg2 equals to, let's say, G4 prime. But in this case, by homomorphism, you can see that this is just square of phi G. Okay, for example. Okay 啊，没问题吗？没问题。Okay, so 小心啊，当你们用这些 statement 的时候 check whether you are proving it or you are using it. Okay, very important. This distinguish what you know and what you don't know. All right. We'll start a very important section in this group theory. Actually, quotient group is the crux of this theory here. OK， 是这个课的精华，难，但是是个精华。OK，so please listen carefully about quotient groups. So you will see some division here now. OK， 哎，wait, by the way， 子豪有问题吗？刚才没有，听得懂我讲吗 ？OK 啊 ，right. So what's the quotient group here? Basically, is the object that we have seen before. So it is the set of cosets. So we now put all the cosets together. But this coset is very special. It's a coset of a normal subgroup. Later you'll see why we only restrict to normal subgroup. Okay. Coset of normal subgroup. So this set of coset we denote as we have two subgroup and one group, right? So we just put G quotient by n. Okay, G 被 n 除了。没有 ，sorry， 我泡了一点东西，有味道，我忘记了，吓到我啊。Okay, so what is G mod n here? So written in the mathematical expression here is what? These are n, an, bn, cn, and so on. Okay, set of coset. Okay, such that blah blah blah, such that. Okay, let's say these ai a1, a2, a3, such that ai is in G. Okay, so these are the set of that coset. Hey, actually, you've seen this example, you know. Actually, you've seen this example. So my claim was, let's see, my claim was, let's look at Z mod 3. Okay, Z mod 3 here. So I claim that Z mod 3 is a quotient group. Quotient by what? Is Z quotient by 3Z. 哎，大家要跟着这个 example 啊，这个是 first example you have to understand, otherwise 你就会 lost 了。OK， 有看到对应吗 ？I take G as a Z and then N as a 3Z. So you need to ask yourself, why this 3Z is a normal subgroup? What is 3Z first of all? 什么是 3Z? 你拿整个 Z 全部乘3 So what do you get? Yes, 3, 6, 9, 12, and so on, and then negative 3, 0, so on. Is it normal subgroup? Normal man, if you conjugate two things by Z. 肯定是 conjugate, 因为它是 abelian. Okay, so normal. But actually, you know about this group here. You know about this group? 很早就介绍给你了。These are the 0 bar, 1 bar, and 2 bar here. OK， 还记得吗？里面有什么东西？我们来 verify 一下。我们现在用新的语言来看这个 group 了。0 bar 里面有什么？应该 n. Okay, in this case, what's the n here? 3, right? So you have 0, 3, minus 3, and so on. 1, everything add by 1. So you have negative 2, 1, 4, and then so on. And then 2 bar, negative 1, 2, 5, and then so on. So if you want to look at it as a coset, what is the coset here? First one is what coset? 哎，赵胜刚才回答一个问题啊，不是？这个 set 等于谁？3Z 那个 n， and then bottom 呢 ？3Z plus 1, and then 3Z plus 2. Okay, so you can see that these equivalent classes are actually left coset. 明白吗？ They are left coset. Yeah, actually they are left coset. Okay, so yeah. So when we study Z3, they are the set of left coset. And then this is an example of quotient group. Okay. 写漏了啊，写漏了啊。哎，我有写名字吗？我还没有 define sub，我还没有 define quotient group 吧 OK, so this is a set of cosets. Later we will define multiplication here, LOC here, and then prove to you that this is a group, which we call quotient group. For now, it's just set of cosets. Okay, set of cosets. Later, we'll name this a quotient group after we define LOC. Is it obvious to you how to define LOC here? So what's the element here? Element here become coset. So 意思说什么？你要拿两个 coset 乘起来等于另一个 coset. Is it clear to you how to do it? Let's say AN, BN multiplied together. Is it a CN? Okay, AN times BN, is it a CN? If you want to make it a CN, what you need to do? 又有交叉了 AN, BN. 怎么办？能够 group 在一起吗？把 N. And so you need to answer this question. Okay, we need to answer this question. All right. So there's some notation here. So let's put some notation here. We will write G bar, okay, for this coset element, and A bar for the specific that coset. Okay. So in this case here, maybe we will write this group as Z bar. Okay, or not? Hey, 看到吗？看到吗？ Okay, we write coset as a representative bar. Okay, we write a coset as a representative bar. Okay, and then G mod N is a G. Notation, later we'll use this notation. So you need to keep this example in your mind. Cannot? Okay, so this notation is following what we know about Z. Right. Okay, continue. So theorem. So what's the theorem here? So let N be a normal subgroup. Okay, and G bar denote the set of coset. So basically is G cross N. Okay, but we simplify the notation. Is the set of coset of N. So the claim is there exists LOC, okay, on G bar, making G bar a group. Okay, 很强哦，这个东西 we can make this coset, okay, such that there's a surjective homomorphism, okay, from G to G bar, whose kernel is N. 哎，还记得这个问题吗？还记得这个问题吗？ Whose kernel is N？ 还记得这个问题吗？还记得这个问题吗？记得这个问题吗？ Every kernel is a normal subgroup, but is every normal subgroup a kernel? We make this pi as having a kernel of the normal subgroup. Okay, whenever you have a normal subgroup, you can do this construction. Okay, you can do this construction. Maybe we write it more clearer here. So here is the G mod N. Okay. 合理吗 ？Let me think. 有意思吗？对你们感觉好像没有意思。Okay, but does it make sense? Okay, maybe it doesn't make sense now. Later we will see how it makes sense. Right. So there exists, right? So here, it says that there exists. There exists means what? You need to produce it. Okay, you need to produce. You need to produce this. So how do you produce this? So there are 4 things to do here. So there are 4 things to do. First, you need to define an LOC first. Okay, define our LOC on where? on G bar. Okay. G bar here meaning the set of coset. How to multiply two coset, get another coset. Okay. And then prove that it forms a group. Okay, prove that this law forms a group. So meaning what? There is identity, there's inverses. Okay, how can a coset be an inverse? And then what else? We have this surjective business here. Okay, we need to prove that. We need to prove that I is a surjective homomorphism. Hey, but I haven't defined the map for you. What do you think? What do you think? What's the map should be? You have element in G. You want to send it to a coset. Okay, let's say you take an element A in G. Which coset you need to send it to? I say, right, do the obvious thing. A go to AH. Okay, so you need to prove that this map is actually surjective. And then, because it's a surjective homomorphism, right? Meaning what? You can reach all the elements in your core domain. Okay, you need to prove it. Also, you can look at the kernel of this map. Because since it is surjective, right, it doesn't mean that it has to be injective. In fact, it is not. And the kernel is as big as n. The n you started with. Why this n involved? Because you're looking at G portion by n. Okay, the coset. Okay, so let's prove this. Okay, it's not obvious, huh? Don't think that it's obvious, but let's see how it works. Right, so first define LOC first. If I give you AN, BN, how do you multiply? How do you multiply? You just multiply, accept. Okay, just multiply, accept. But why it works? My claim is this is equals to AB times N, the coset of AB. Why it works? How about I write using associativity first? I put NB together, UB. Okay, put NB together. Can we do something to NB or not? N is what? There's only one condition on N. N is what? Normal. Normal subgroup satisfy what property? NB equals to Bn. Or we can. But what is NN? N is a subgroup. So enclosed. Okay, so NN equals to. So meaning what? If you multiply two cosets together, you send to a coset with the product of the representative. Okay, you send to the product of representative. Okay. Are we good on this? Yeah, I think we are good on this. Right. Next, why is it a group? Okay, let's after define this. Why is this a group? So what's the identity here? Who is the identity? What do you think? Who is the identity? What's the coset that you multiply to another coset you get back? Joseph. N, right? Because N is the identity. Because what? You need to check two direction, right? N, AN equals to AN equals to AN times N. Okay? So one direction here you use subgroup. The other direction you use what? N is a normal subgroup. Okay? Okay, so normal 是这样子用的，我们可以 swap 的。Not elements wise, but set y we can commute. 明白吗 ？OK， 有一点像 commutative 的，但是呢，它又不是每一个 element 都是直接交换，而是整个 set 可以直接交换。OK， 所以 normal 是有一个很像 Abelian 的一个东西。OK， 但是又不是。OK， right. So we have identity. How about inverse? I think pretty obvious, right? So what's the inverse of AH? AN, sorry. What's the inverse? A inverse N. Okay. A inverse N. Okay, no? Okay. So if you multiply left, multiply right, you get A inverse AN and then A inverse AN and then A inverse N. Okay, so two directions. Both directions you get. Okay, so good is a group. 哇，很快一下哦。How about a normal? Okay, we finish this and then I think we will finish this class. I won't drag you. Okay, so why is this a surjective homomorphism? Surjective homomorphism, how many things to prove here? Surjective and homomorphism. Okay, so we need to do two things. So let's see what's our map here. Let's write it out. So we send A to AN. Why is it a homomorphism? What do you need to check? Pi of AB equals to pi A times pi B. So what happens in the middle here? Under this map, AB gets sent to ABN. Okay, but if you go from the other side, you have AN times BN. But we know that the N is normal. So we have AB and N. Okay, so it's a homomorphism. Why is it surjective? Why is it surjective? Meaning what? For every left coset in G bar, not G prime or G bar, we need to find what's the pre-image. What's the pre-image? What's the thing that gets sent to AN? 子涵 What's the thing that sends to AN? 不知道这个 map 在干嘛哦 ？A 去 AN 对啊 ，You just pick the representative of this coset. OK 吗？明白吗？ So let me write here the pre-image of AN is exactly the representative of AN. Is exactly, I mean not exactly, one of them is okay, right, this one of the pre-image of AN is the representative A of AN. Okay, we just pick the representative. Make sense? Okay, so now last job. Okay, our last job here is to show that I want to show kernel of pi equals to n. Okay, kernel of pi equals so equals as set equality. You need to show two directions. Okay, so I claim that one direction is easy. Which direction? 来，你们要知道一下，哪一个 direction is easier? N to kernel or kernel to n? Which direction is easier? Any idea? 猜一个也可以。对，来，我们让一个很久没有来的老朋友来回答一下。Sorry, N to kernel of pi easier or kernel to n easier? 没有声音？不会不用紧，我让你猜吧。你不会的东西啊，我们怎么学？我们就是从猜开始，猜先，猜久了你就会有感觉啊。 OK， 先猜先，你一定要猜，猜是第一步，好不好？一定要猜，来，两个罢了，选一个吗？来选一个，错不题啊，左去右啊。OK， 答案是右去左啊，常常都是这样的事情发生。然后你就要想一下为什么右去左容易啊？现在专心听啊。So why why this one is easier? Kernel n is in kernel of pi. What do you need to check here? You need to check what happens if you apply pi to all the element in n. What happened? It is just n. Why? Why? For every n in n, where do I send pi n to? I send it to n, n. But n is in n. So n is n. Okay. I purposely don't say capital or small n. You should know what is it. Okay, because it's a subgroup. Okay, how about the other direction? The other direction is usually tricky. So second, 这个就是右去左啊，比较 tricky 一点。Suppose S is in the kernel of pi. This means what? Stay in the kernel of pi meaning what? Pi x is what? Equals to, what's the identity here? What's the identity in this quotient group? Is n. But, what do you know? Pi x is also equals to xn. So this means what? Sn is equals to n. 然后呢? Can we deduce that x is in n now? 为什么可以啊? Oh, the TFAA statement. Do we have this statement? What's that statement say? And the new bn. Wait. A and the new bn implies A should be bn. Okay, good. Okay, so but this is true only if x is in n. Okay, because n is a subgroup. Okay, so this implies that kernel of pi is in n. Okay or not? Okay, 谢谢. Okay, so from here we will define that G mod n is a quotient group of G by n. Okay. Since okay, so it forms a group. So set or coset of normal subgroup form a group. Okay, only normal. Let me give you a remark here. So let me give you a remark here. Let's say you take this subgroup here, h equals to 1, 2, generated by 1, 2 in x3. You can look at h times, for example, the left coset 1, 2, 3 times h. Okay, and then if you do this, there are 4 elements here. 1, 2, 3, 1, 3, and then 2, 3, and then 1, 3, 2. And this is not a coset of h. Can someone quickly see why is this not a coset of h? Yensen, do you know why? No? How many elements inside a coset? What's the number of elements inside a coset? 还记得 h 吗？怎么切那个蛋糕？ It divide the group equally. Okay, what's the number equals to? The number of elements in your subgroup. But This subgroup has how many elements? Only 2. But if you multiply these 2 coset together, you get 4. So it's not a coset of H. Okay, so if it's not normal, so this one is not normal. It's not normal. Not normal in X3. So you don't get this nice LOC on this coset. Okay. You only can get nice LOC when the subgroup is normal. Okay. Any question? So we will spend some time talking about this quotient group. And then we will do fun stuff on free group. Okay. Yeah. So any question you want to ask me before we finish? About exam also can. Next week we still have next week, yeah, right, next week. Next week office hour, right? Tuesday don't have but if you want to come to the room to do homework, you still can. Some of senior maybe will be there because I will be having calculus 2 exam that time. Okay, and then Wednesday we will have a usual office hour. And then Thursday exam. Now this timing in a different room, don't come to this room, this table not nice. Okay, so we go to A4. And then Friday, try and see if you can submit assignment. Otherwise, we discuss next week. You try first. Only 2 questions. Okay, so try first. Okay, so see you next week.